In the last video, we took a look at defining the field of physics, and we explored defining quantities operationally. We came up with that there were 7 quantities that we considered to be base quantities that we had to define operationally. And we'll take a look at some of those quantities here. But first, I just wanted to get a little bit into units of measurement and talk a little bit about the revisions that were done to Système International, the metric system, in 2019. So first off, just as a quick pause and ponder here, I'd just like to ask you, what is the point of having units? Why do we have things like pounds or kilograms or arsheens or whatever? Okay, the reason that we have them is just simply to facilitate communication. It doesn't matter what the units are as long as we all agree on what they are. So for instance, if you look at the weather report and that you see that the temperature outside is going to be 30, you know that you're probably going to want to wear a t-shirt and some lightweight clothes or something like that. Oh, wait, were you thinking that you wanted to wear a winter coat? So the difference there, of course, is 30 degrees Celsius is a nice, warm, comfortable day. And 30 degrees Fahrenheit is going to be a little bit below freezing, probably going to want to bust out the winter jacket. It doesn't matter. It's not necessarily that one is better than another, although I'm personally probably more of a fan of Celsius than anything. But it doesn't really matter that one's better than another. It just matters that we agree on what it means, so when someone says it's 30 out, we know how to dress. And same is true for anything else, any unit of distance, anything like that. We all have in the back of our minds some sort of agreed upon standard that we go with. Now, and with that standard, we can facilitate communication with each other. So the major unit system out there is called Système International, and my apologies to anyone who can speak French at all, because I'm sure I butchered it. Or we usually just call them SI units. That's really the official name for the metric system. And in the United States, actually, this is our official units of measure and have been since the end of the Civil War. But more on that later, in case that came as a surprise to you. What I do want to do is spend just a quick moment in case in any prior exposure you had run across the definitions of the SI units. I want you to be aware that there was a major overhaul to the system. It was designed to be back compatible, but the system was overhauled substantially. And it was adopted on May 20th, on 2019. May 20th, that was the anniversary of the year that the International Treaty of the Meter was signed by a large percentage of the world, where everyone agreed that they would use metric units. And so just to give a bit of a flavor for how it's changed, in case this is the first time you've run across it, I just want to spend a quick moment talking about time and length. So time is one of our base quantities. So it's a thing that a clock measures. Well, what units do we usually use? Well, it turns out the usual unit we use is the second, and the symbol for second is just a lowercase letter s. Now, the current definition is based on the observation that, as near as anyone can tell, certain intrinsic properties of atoms do not change with time. And so in the current definition, this quantity right here is defined to be the frequency at which light gets emitted from a certain hyperfine transition of the cesium-133 atom. Now, we don't have to worry about what a hyperfine transition is, but suffice it to say that it is entirely possible to get light to come out out of cesium-133 with this particular process. And what we've come to realize is that the frequency with which the light gets emitted, how many wave crests of this light pass a detector every second, with lots and lots of careful measurement, we've seen that this never changes. And so what we've now done is said, okay, we are going to assume, we're going to roll with that and say that it doesn't change. And so we will say that the frequency of this particular light is 9,192,631,770 cycles per second. So a way that you could measure a second is to build a device called an atomic clock, where you have a collection of cesium-133 atoms that you drive into this hyperfine transition. And you look at the light coming out and you count the crests of light passing your detector. And you just literally start going 1, 2, 3, 4, 5. And when you get up to 9,192,631,770, you say that a second has elapsed. Now, this barely differs from the pre-2019 definition, but it's an important distinction. In the pre-2019 definition, the second was defined by saying as the amount of time that elapsed when that many crests of light went by. Now what we're saying is no, the frequency of the light is this, and from that you can measure a second. So for instance, you don't have to build a clock now using cesium-133. You could, for instance, use rubidium, build a rubidium clock that measures these properties of cesium, for instance, and that would be fine. So this definition does not depend on an exact experiment. Now, the Bureau International de Poids de Mesure, the International Bureau of Weights and Measures, who's responsible for enforcing the International Treaty of the Meter, will publish circulars that say what they think the current best experimental practice is, and they're still recommending you build cesium clocks for now. But maybe what will be a little clearer with this is if we look at at mass. We'll get more in a later video series. We'll get more into what mass is. But for now, it's the thing that we measure with a balance, and the units of mass are the kilogram. Symbol kg. So, I'm sorry, don't want to do mass just yet. My apologies. I'll get to that in a second. Let's do length first, and then we'll get to mass. So let's look at length. Over time, length has had a bit of an interesting history. It started out as a certain fraction of the distance between the equator and the North Pole. Turned out that this was incredibly hard to survey, and so when they made a prototype platinum iridium rod, it wasn't that fraction because the surveying work wasn't as good as hoped. So that unit would be the meter, symbol M. So eventually it's like, well, the problem with that rod is quite literally if someone drops it, that would be really bad. So the hope was to find some way of doing it that didn't involve the rod. Eventually, people very precisely measured that rod using a Krypton 86 laser instead of so many wavelengths long. And then there was another definition that came after that. But now with the current definition, the speed of light is set to be an exact number. It's 299,792,458 meters per second. And this is because, as best as we've ever been able to tell, the speed of light is a property of the universe that does not change. Now, if you can already measure a second, the meter pops right out from that, because you say, oh, hey, it's the distance that light would have traveled in some split second. So now, instead of using particular experiments to define the meter, it's buried into the fundamental property of the speed of light, and the meter gets defined in terms of the speed of light. Probably the most dramatic of the changes is, however, mass. And like I said, we'll get more into what mass is in a later video. Its unit is the kilogram, symbol kg. And literally all the way up until May 19th of 2019, it was defined as the mass of a certain metallic object kept in France. Any attempt to do a better job just ran into too many technical hurdles. And there was a bit of a crisis. It turned, this metal object in France only got pulled out of its vault like every 20 to 30 years for comparison to copies kept around the world. And the last time it got pulled out of the vault, all the copies in the world had drifted in the same direction. Now, what that probably means is that the actual master was mishandled somehow. But since by definition the kilogram is whatever the mass of that object in France is, literally we had a very small, it didn't matter much practically, but we had a very small change in what a kilogram was. This has now been resolved in the new definitions by defining a quantity from quantum mechanics called Planck's constant to be exactly equal to this number. Now, you see joules and seconds here. This turns out to have nothing but kilograms, meters, and seconds in them. So the second gets defined from the frequency of this particular kind of light being exactly this. The meter then gets defined in terms of that second. And now the kilogram gets defined in terms of both the meter and the second. And there is a new best practice experiment. It's a device called a kibble balance, or also known as a watt balance. Can now be used to measure very precisely what the mass of reference objects are. And that is the new definition of the kilogram going forward. With this redefinition, the last of the last of the artifact standards are called, things that couldn't be done by experiments in the lab, have been retired. Just real quickly, we'll see that the Kelvin of temperature, we'll get to this more when we get to the unit on thermodynamics, has now been defined in terms of thermal energy through a number called Boltzmann's constant. Avogadro's number is now an exact number, and the charge on an electron is now an exact number. And also luminous intensity is precisely defined, but that won't matter unless you're a professional optician. Okay, so I mentioned this mostly just because it may be news to some of you that things have gotten redefined. And the beauty of this is that it should never need to be redefined again. Everything is now based on an inherent fundamental property of the universe, which is actually nicely having gone full circle from where we started. The metric system was originally defined based on properties of the earth and water. It turned out there were an awful lot of technical issues with those, but now instead of letting, but we at least get back to the idea of let nature define the units. So instead of using the earth, it's the entire universe. So say if we were to make contact with some advanced civilization, we could completely describe our unit system by just simply transmitting these physical constants to them, and they would be able to relate it to whatever unit system they were using. Okay, now I did mention that the United States was the 13th signatory of the International Treaty of the Meter, and so for well over a century we have been officially a metric nation. Now, this may come as a bit of a surprise to you, but the way it got implemented in the US was a creation of what were called standard American equivalents. So, by law in the United States, a foot is defined to be exactly 0.3048 meters. No more, no less. And similarly, quantities like the pound and everything else are defined by similar exact multiples of the corresponding metric quantities. So this is mostly done in order to make things a little more convenient, historically. So after all, if you're used to buildings, having their joists so many inches apart, right? It was just a way to keep on that same footing while being officially a metric nation. There was actually an attempt in the 1970s to get the commercial side caught up to the legal reality. And basically the U.S. mapped out a plan to do this over 10 years. That took way too long. Canada ripped the Band-Aid off in 1 year, and now they are a metric nation. We tried to rip the Band-Aid off too slowly, and everyone said, well, let's just stay where we're at. But this is why, for instance, when you go and buy pop at the store, you buy it in liters. That's because the transition was targeted industry by industry, and the beverage industry was one of the very first that was targeted. Okay, so with that, let's spend a little bit of time on doing some unit conversions. And I'll start by talking about metric prefixes. So let's say you have a distance like 17 kilometers. Like 17 kilometers, like so. When you look at the symbol that comes after the 17, it actually comes in two pieces. The M here is actually what's known as the symbol. That's the meter part. And then the K here is what's called the prefix. And literally all you should think of when you see the kilo prefix is that it means times 1,000. So for instance, if you have 17 kilometers, you would write that as 17. Then when you see the K, that's the same thing as times 1,000. meters to give you 17,000 meters. And similarly, if you have a prefix like, say, centa, let's say you're dealing with a length of 42 centimeters, the centa prefix should always just be replaced by divide by 100. So 42 centimeters, sorry about that, 42 centimeters would be 42. When I see the C, that means divide by 100, and then I'm left with the symbol M. So 42 100ths of a meter, or 0.42 meters. And with the exception of the kilogram, because we do not write kilograms. So even though the official base unit of mass is the kilogram, for historic reasons, what we do is we pretend that the base unit is the gram. And so the G in kg is the symbol, and K is the prefix. But officially it's defined around a kilogram, not around a gram. So a few of the more common prefixes that you're apt to run across. A capital M, doesn't matter what it's in front of, is going to correspond to times a million. A lowercase k, that's mega. A lowercase k is kilo, that's times 1,000. When we get to pressures, you might run into hecto. That's times 100. And then a lowercase c is centa divide by 100. And a lowercase m is milli divide by 1,000. And the system of prefixes goes down to smaller than the smallest theoretical objects that physicists worry about, to bigger than bigger than the entire universe itself, regardless of what property of the universe you're measuring. But we won't get into some of those more crazy ones. So, okay, so if you're going just back and forth between prefixes and the metric system, this will get you everywhere you need. But if you do have to go in and out of, say, standard American equivalents, that's where repeated multiplication by 1 is useful. So for instance, let's say that you have some object that's going at 14 furlongs per fortnight. And we would like to get that into some number of meters per second. One way you can do this is just to keep setting up a ridiculously long fraction. So we'll start by writing what we have. 14 furlongs per 1 fortnight. And then what we'll keep doing is we'll keep multiplying by fractions that are officially the number 1, but they're written as the number 1 in ways that are more useful to try to get us to our target unit. So for instance, let's work on this fortnight. We know that a fortnight is 2 weeks or 14 days. All right, so now with that, we can go ahead and cancel the fortnights. We've got 14 furlongs per 14 days. Cool. All right. Now, though the day is closer to being a second than a fortnight was, so that's some sort of progress. We might sit and think, well, what's closer yet? We might say, oh, how about an hour? So 1 day is 24 hours. So we put the day in the numerator so we can cancel the day in the denominator there. We'll be left with an hour in the denominator there. So let's go ahead and cancel the days. So now we've got an expression that works out to furlongs per hour. All right, I think you see where this is going to keep going. We'll take hours into minutes, for instance. 1 hour is 60 minutes. And 1 minute is 60 seconds. So with that, we can go ahead, cancel our hours, and then we can go ahead and cancel our minutes. And hey, we're down to furlongs per second. Woot. All right, well, this is going to be going on for a while, so let me continue the fraction down on the next line here. So we've now gotten from fortnights to seconds. Cool. Now we need to get from furlongs to meters. So we of course remember that a mile is 8 furlongs, right? So that will let me cancel furlongs, be left with miles. And then we remember that 1 mile, again, the mile here is in the denominator, so I can cancel this mile in the numerator, is 5,280 feet. All right, so that will let me cancel miles. And then we remember that in the US, a foot, by definition, is exactly 0.3048 meters. So we can cancel feet, and we are left with our target unit of meters. All right, so now the trick here is we've got our meters and we've got our seconds left. So what you do is you multiply all the numbers together in the numerator. So it's going to be 14 times 5280 times 0.3048. And we'll divide by the product of all the numbers in the denominator. So it's 14 times 24 times 60 times 60 times 8. And we were left with meters per second. And if you crunch this through on your calculator, 14 furlongs per fortnight is 0.0023 meters per second, or 2.3 millimeters per second, if you prefer. All right. So if you're just converting individual powers of units, that's how you would do that. But let's just see what happens if you have to deal with powers of units. So for that, let's convert an acre into square meters. Because remember, it's a unit of area. It's in area's length times width, so it'd be a meter times a meter, so that's meters squared. Well, so we start with 1 acre in the numerator, nothing in the denominator. By definition, an acre is 43,560 square feet. Now, so far so good. We've canceled our acres. Now we need to convert our feet into meters. And we remember that 1 foot is 0.3048 meters, so we're good to go, right? Wrong. Because what that will have done for us, it'll have gotten us somewhere, but it'll have only canceled one of these powers of feet. So now we have feet times meters. So we have to convert the other power of feet as well. So we're going to have to multiply by another fraction of 0.3048 meters per 1 foot. So now that will cancel the remaining power of feet. And now you see here I have meters times meters upstairs. So that gives me the desired square meters. That's our target unit. So what do we have? We've got 43,560 times 0.3048 twice, so that's squared. And then when we have meters times meters, that's meters squared. So it turns out to be 4,046.86 square meters. Awesome. All right, in the next video, we will start to hang numbers onto physical properties like position, displacement, and velocity to get a beginning of a definition there. Catch you in the next one.